In this video, we are continuing section 9.3, the instantaneous rates of change, and we are ready for example 5. In example 5, it says the distance an object travels from its starting point in feet is given by the function s of t equals 11t squared plus 4t plus 2. Find the velocity of the object at t equals 0 and t equals 5 seconds. Why do I know that I need to find the derivative? Because of the word velocity. As soon as you see velocity, you know that you need to find the derivative. Let's begin our 4 steps. On the first step, we are going to do, the name of our function is s. Now notice that our variable is not x, it's t. So instead of doing x plus h, we are going to do t plus h. This equals 11 times t plus h, which we are squaring, plus 4 times t plus h plus 2. Remember that t plus h quantity squared will be t squared plus 2th plus h squared. That's this part. And then we have to take it times 11. We are then going to have 11t squared plus 22th plus 11h squared plus 4t plus 4h plus 2. So we got a really long answer for step 1. And if you look at all of those items, none of them are like terms, so they have to stay as is. Moving on to step 2, we have to take s of t plus h minus the original function. So we're going to take our answer from step 1, 11t squared plus 22th plus 11h squared plus 4t plus 4h plus 2, and then we're going to subtract that entire original function. In doing that, we need to change all the signs, so it will become minus 11t squared minus 4t minus 2. Remember that this is the step where your non-h terms must cancel. 11t squared and negative 11t squared cancel. 4t and negative 4t cancel. 2 and negative 2 cancel. We are then left with 22th plus 11h squared plus 4h. All of the terms that are left have h's in them, and so we know that we are okay because you must have an h in every term. For step 3, we want to take our work from step 2 and put it over h. So we are going to have 22th plus 11h squared plus 4h all divided by h. There is an h in every term, so we're going to take out the smallest power. We're going to take out 1h from each term, which will leave us 22t plus 11h plus 4. Step 4 says to do the limit as h approaches 0 of all the stuff that we just did in step 3. So we are just going to do the limit as h approaches 0 of that answer that we got, 22t plus 11h plus 4. This is polynomial in form, so we are going to put 0 in for h and stop writing limit. We will get 22t plus 11 times 0 plus 4, which simplifies to be 22t plus 4. Once we have that final answer on step 4, that is the derivative. So this is s prime of t. This application was velocity, so in this case, this is our velocity formula. But we weren't asked just for the velocity formula. We were asked to find the velocity at t equals 0 and t equals 5. So at t equals 0, velocity is 22 times 0 plus 4, which is just 4. Now labels, you do distance. What were we measuring our distance in? It was feet. Per time, our time was being measured in seconds. So what we know about this, even though it didn't ask it, we're going to talk about how this is interpreted. What we know is that the speed or the velocity is increasing by 4 feet per second from 0 seconds to the next second, 1 second. That's how you would interpret that answer. The other thing that we know, because it is positive, it is moving forward. So let's look at the other that we were to do. We were supposed to do at t equals 5. Our velocity at 5 will be 22 times 5 plus 4. That will give us 114. Again, our label will be feet per second. So we are moving forward at 114 feet per second from 5 seconds to 6 seconds. On example 6, we are told for the function f of x equals 2x to the third minus 6, find the formula for the slope of the tangent to the graph at any point. Find the slope of the tangent at x equals 3. Write the equation of the tangent at the point 1, negative 4. If you go back and look at this, you will see that we actually have 3 questions here. The first question starts right here with find the formula for the slope of the tangent. Our second question starts here. Find the slope of the tangent at x equals 3. Our third question starts here with write the equation of the tangent. So we've got 3 things to do here. First, we want to find the formula for slope of the tangent. What is it in the wording here that's telling me find the derivative? This phrase right here, find formula for slope of the tangent. That's what's telling me find the derivative. So for step 1, we need to do f of x plus h, which is going to be 2 times x plus h, which we must cube, minus 6. The reason that I'm doing this problem with you is because I am not going to ask you to, on your own, do the third power of x plus h. I'm going to write it down in here so that you have it. The third power of x plus h to the third is x cubed plus 3x squared h plus 3x h squared plus h cubed. Again, I will not be asking you to do that ever. So now what we need to do, going back up and look at our formula going up here, we've got to take that cube of x plus h times a 2. So we will get 2x cubed plus 6x squared h plus 6xh squared plus 2h cubed. So that finishes all of this part. Now we need to tack on our minus 6 for the end. So that's the answer for step 1. Now step 2 says take this answer that you just got and subtract the original function. So we are going to have 2x cubed plus 6x squared h plus 6xh squared plus 2h cubed minus 6. Now, subtracting the original has the effect of changing the signs. So we will have minus 2x cubed and plus 6. This is the step where we have to have some canceling happening. Positive 2x cubed, negative 2x cubed, cancel. Negative 6, positive 6, cancel. Every term that's left must have an h in it. We get 6x squared h plus 6xh squared plus 2h cubed. For step 3, take the answer from step 2 and divide it by h. We will have 6x squared h plus 6x h squared plus 2h cubed divided by h. Since there are h's in every term, you take out the smallest power that appears. The smallest power that appears is h to the first. So we're going to take one h out of each term. So we take the denominator out. We take out the h from the first term, take out one of the 2 from the second term, and then take out one of the 3. So we still have 2 left on that third term. What we now have is 6x squared plus 6xh plus 2h squared as our answer for step 3. Step 4 says take the limit as h approaches 0 of the answer that you just got, 6x cubed plus 6xh plus 2h squared. If I put 0 in for my h's, I will have 6x squared plus 0, which is just 6x squared. Once you are done with step 4, you have your derivative. Our original function was f, so this will be f prime of x equals 6x squared. What was our application in this case? Slope of the tangent. So this is formula for slope of the tangent, which is what question 1 was asking us to find. So we are done with question 1. Question 2 said, find the slope of the tangent at x equals 3. This was question 2. So all we need to do there then is find f prime of 3. If we put 3 into that, we will have 6 times 3 squared. 3 squared is 9 times 6 gives us 54. So the slope at x equals 3 is 54. Question 3 says, write the equation of the tangent line at the point 1, -4. So if we're writing the equation of a line, we need y equals mx plus b when we are done. We need to know a point and the slope in order to get there. We know the point. It was given to us. Here's our point. What we don't know is the slope for this tangent line. But we know the formula for slope of the tangent line. We know that it's 6x squared. So to find our slope for the tangent line we are talking about, we are going to use f prime of x equals 6x squared. In order to find the slope, what does our formula require? It requires x. And if you look at our point, we know the x value, we know it's 1. So we will do 6 times 1 squared and get 6. This gives us the slope of that tangent line. Now we know the slope of our tangent line and we know the point at which the line is happening, so we are ready to write the equation of the tangent line. It is not wrong to use y equals mx plus b, which I know a lot of you have done. What I have found, though, is that students use y equals mx plus b and then they forget to actually write the equation for the line. They find b and then forget to finish it. So what I tell students to use to avoid that mistake is use point slope formula and point slope formula for a line is y minus y sub 1 equals m times x minus x sub 1. You have all seen this at some point. You may have forgotten about it. You haven't done it for a while, but you have all seen this. If you took algebra, you've done it. When you are looking at this formula for a line, this y, the first y and the first x, stay in there as variables. What you sub in for are y sub 1, x sub 1, and m. There's your point and your slope. Remember, m is slope. So for our problem then, we are going to keep the y variable minus y sub 1 just means the y of the point. The y of our point is -4 equals m. What was the slope? What did we just say our slope of our tangent was? We said up here it was 6. So we're going to put 6 where the m is. And then in our parentheses, we're going to keep x as the variable minus the x of our point, which was 1. Clean this up a little bit. You're going to get y plus 4, and then distribute on the right. You're going to get 6x minus 6. Subtract 4 from both sides, and you get y equals 6x minus 10. So what we found here now, this is the equation of the tangent line at the point of 1, -4. The last thing we need to talk about for section 9.3 requires talking about the word differentiable. So before we even start using that word, let's talk about what it means. The word differentiable means has a derivative. So not every function is differentiable at every point. A function is not differentiable where there is a discontinuity, a corner, or a vertical tangent. And so in the figure that I have given you here, I have shown you what the various things look like. Discontinuity, we've already talked about being continuous or not. Anytime a function is not continuous, you cannot do a derivative at that point. A corner means that you have lines coming in and creating a sharp point. When you have that, there is not a derivative at that corner. Vertical tangents can happen in two different ways. The first way you might see a vertical tangent is when the graph itself appears vertical for a moment. When that happens, then there is not a derivative at that point. The other way you might have a vertical tangent is if you have curves coming in and creating a sharp point. Again, there is not a derivative at that sharp point. On example 7, we are to use this given graph to decide where the function is continuous and where the graph is differentiable. Notice that it says where it is continuous and where it is differentiable. So we're going to say the places where it works. When that happens, we write our answers in interval notation. And interval notation always goes from x value to x value. So let's look at continuity first. Where is this thing continuous? Just be real systematic about it. Work from the left to the right, because you're starting from -infinity going left to right, the way we would read. This thing would go to the left forever. That's got an arrow on it. So we are coming from -infinity. Anytime you write an infinity, you must put parentheses around it. So let's think about how far could I trace this before I'd have to pick up my pencil. So I'd start at -infinity, and I would be able to just keep tracing this thing until I got right here. What x value is that happening at? That is happening at -1. The thing you need to notice about what's happening there at that upper part of -1 is that it is a solid dot. So we would have to put a bracket around it to show that it was solid. Now, where do we pick up? We pick up down here with the open circle and would continue. Where is this open circle happening? It's also happening at -1. So we're going to start again at -1, but because it's open, we're going to put a parentheses. Now we're going to start another section of where this thing is continuous. So when you have more than one section, what you put between them is a U, standing for union. This just also means, and also this section. So where did I have to pick up my pencil again? Up here. Where's that? What is this showing me? It's showing me it's going down forever and it's going to get closer and closer and closer to that vertical axis. What x value is the vertical axis? It's 0. So we're going up to 0, but we're not touching 0. It's not included. So we get a parentheses around it. We have to write another section, so we're going to put U in here. Where do I pick up again? I pick up on the other side of 0. This thing has come closer and closer and closer to 0, so I'm picking up again at 0, but I'm not including it because it was my asymptote. Where do I have to stop for this open circle? What x value is that happening at? That's happening at 2. It's an open circle, so I put parentheses. Now we're going to have to write another section. Once we get through 2, then we stay, and we can just keep tracing the rest of it without ever picking up our pencil. So we start again at 2, but we don't include it because it was an open circle. And we go on till the end of the graph, which goes to infinity. So those are the what we call intervals for which this graph is continuous. So let's get rid of these marks. And now we need to talk about where we are differentiable. Remember, that word means where do we have a derivative. So just like before, we start by coming from negative infinity, but we're going to hit a problem right here. This dotted line is showing you a vertical tangent, and we said that we are not differentiable at vertical tangents. So from negative infinity, we are good until we get to negative 3. Now we don't include it because there's not a derivative there. So we put a parentheses around it. Now we're going to continue on. Now once we get past negative 3, we stay differentiable until we get down here where we'd have to pick up our pencil. Remember, any place that it is not continuous, there is not a derivative. So we are differentiable from negative 3 to negative 1. The place where negative 1 is solid would have a derivative. So we're going to put a square bracket. But then on the other side of negative 1, where it's open, there would not be a derivative. So we're going to put parentheses, negative 1, and then what's happening again, from negative 1 here, we're going to take another break. We're not going to be continuous there. So from negative 1 to 0, we do have derivatives, but once we hit 0, there is not a derivative. Then we pick up on the other side of 0, and we do have a derivative until we hit a discontinuity. So we are good from 0 until we get to the x value of 2, where we have a discontinuity. So there would not be a derivative at the 2. Then we're going to pick up on the other side of the 2, and we hit this point here at the x value of 3. Anytime you have a sharp point, whether it's created by curves or by lines, there is not a derivative there. So we're good from 2 to 3, but then there's not a derivative at 3. Then we continue on from 3 until we hit another sharp point over here at 5. So there is not a derivative at 5, but there is between 3 and 5. Everything will have a derivative. And then after we leave 5, the rest of the graph is good. So our last place where we do have derivatives is from 5 to infinity.